Check this out. We've got something really fun today. This is so amazing. Oh man, again? 10.2, area between curves. We found the area between a curve and the x-axis and called this area under a curve. Now we would like to find the area between curves. So this area here, a of x, can be found by finding the area under f of x and then subtracting the area under g of x like this. We have the area under f of x, which goes all the way down to the x-axis. We've got the area under g of x here, and we're going to subtract them, and that will just equal the area between the two curves and bounded by some lower and upper bound. So we have this, the area under f of x, and we have this, the area under g of x. And if we distribute in the negative sign, it would look like this. Often it's a good idea to put the functions together and simplify them into a new function if they share common terms. And we could say that would be a new function h of x. And so we just need to reorder this and put both of the b's here and the a's here together. And then you see this is h at b and this is h at a. Find the area in between the curves y equals x squared plus 1 and y equals x from x equals 1 to x equals 3. The first thing we should do is get a sketch of what this area looks like so we can tell which function is higher than the other function. So this one's a parabola. It opens up. It has a vertex at 0, 1. So it would look something like this. And then we have this function y equals x, and it would look something like this. So you can see that the parabola is higher, so we'll be subtracting this linear from the parabola. And we're going from x equals 1 to x equals 3, so something like this would be our area. The next thing we need is the antiderivatives, and they're both called y equals, so I'll refer to this one as f of x. So the antiderivative is capital F of x, and that would be x cubed over 3 plus x. This one here, we'll say this one is g of x, so the antiderivative is capital G equals x squared over 2. Now in this case, none of these terms will cancel out, so there's no advantage combining these. Let's just find the area under y equals x squared plus 1, and that would be capital F at 3, because that's our upper bound, minus capital F at 1, because 1 is our lower bound. So we put 3 into this equation here, so 3 cubed divided by 3 plus 3 minus, and I'll put it in brackets, 1 cubed over 3 plus 1, close bracket. 27 divided by 3 is 9, plus 3 minus a third and minus 1 when we distribute in the negative sign there. And then we got 9 plus 3 is 12, minus 1 is 11, minus a third would give us 10 and 2/3. Now let's find the area under y equals x. So we'll use capital G at 3 minus capital G at 1. And we just put a 3 in there, so 3 squared over 2 minus 1 squared over 2. And this would be 9 over 2 minus 1 over 2, and that would be 8 over 2, which is just 4. And now we can finish by finding the area between the curves. And so this one is higher on the graph, but we can also see that it's larger, so that makes sense. So we would have 10 2/3 minus 4, and that would be 6 2/3 units squared. Find the area bounded by the curves y equals x squared minus 2x and y equals 4 minus x squared. They're not giving us an upper and lower bounds, so we need to find where they intersect. And we're going to do that by setting them equal to each other. So 4 minus x squared equals x squared minus 2x. Looks like, let's go on this side, so plus x squared on both sides, 2x squared, minus 4 on both sides, and we get this. So now we can just solve this quadratic. Let's divide the entire equation by 2, and that will give us x squared minus x minus 2. And then it looks like we can factor this to find the solutions. So we'll say x, probably a minus 2, and x plus 1. That means that x equals 2 and negative 1. Okay, so that's where they intersect. Now, let's draw a graph. And then we can tell which one's on top and what bound we're talking about here. So this is my y. Here's my x-axis. This one here, let's see, factor out an x and I get x minus 2. So I've got x-intercepts at 0 and positive 2. And that's going to be where actually they both intersect. This one opens up, it's got a positive leading coefficient, so I know it's doing something like this through there. This one here, it's got a negative leading coefficient in front of the x squared, and 4, so that means that my y-intercept is 4. So 1, 2, 3, 4, and my x-intercepts are at negative 2 and positive 2. So this graph comes up here. It's that point and comes back down. Okay, so I can see that there's a nice area in here that these two functions surround. So just can see that this point here is my lower bound, negative 1, and at this point here is my upper bound, positive 2. So now I can go and find the areas under those curves. Looks like the one that's opening downwards, that will be the higher one, and we'll subtract this one here, the lower one. Now, when we're looking at this, this does dip below the x-axis, and that would be calculated as negative area. In this question, it's going to work out perfectly, because think of this, we've got this area here, which doesn't include that, and it does include this. And we're going to subtract the area under this parabola. It's going to subtract this positive area, and it's going to subtract a negative area here. And subtracting a negative area will actually mean it's going to add that area there. So this will work out perfect. So let's find area under y equals 4 minus x squared. So I'll call this one f of x, and its antiderivative here will be capital F of x then, 4x minus x cubed over 3. And we want the area from negative 1 to positive 2, so we want to put in 2 into our function here, and then put in negative 1. So 2 times 4 minus 2 cubed over 3 minus, put this in brackets, 4 times negative 1 minus negative 1 cubed over 3. Now we've got 8 minus 8 thirds. This will be negative 4, and we distribute this in, it'll be positive 4. This one is negative 1/3 times this negative, it makes it positive, times this negative makes it negative again. Okay, so we got 12, and then minus 9 thirds, and that would just be 3, and 12 minus 3 is 9. Let's go do the area under the other function. So area under y equals x squared minus 2x. X squared minus 2x. We'll call this one g of x, so its antiderivative will be capital G of x equals x cubed over 3 minus x squared. Now we want to do the same area interval, so -1 to +2, so g at 2 minus g at -1. Now g at 2, let's see, 2 cubed divided by 3 minus 2 squared minus brackets -1 cubed over 3 minus -1 squared. This one here is 8/3 minus 4. This will be -1/3 times this negative is +1/3. And this one becomes positive and then negative and then positive again. So all of this, oddly enough, is equal to 9/3, which is 3, minus 4 plus 1 equals 0. So all that's saying is that this area right here, this little triangle thing here, and this little half circular shape here actually were exactly the same. And so they canceled each other out and made it 0, which means that the area between the two curves is 9 minus 0. So it's 9 units squared. Find the area between y equals sine x and y equals cos x from 0 to pi over 2. Now that's quadrant 1, and we know in quadrant 1 that cos starts off at its maximum and sine starts off at 0, and then halfway through quadrant 1 they are equal. Now cos would be initially the higher function here, and it is graphed in blue. And then at pi over 4 they are equal. After that, sine becomes the higher function. Now the problem with this, and what we're trying to do, is that the functions change halfway through here which one's on top. So if we had to do this the long way, we'd have to take the area under cos x from 0 to pi over 4, subtract the area under sine x from 0 to pi over 4. Then we'd have to take the area under sine x from pi over 4 to pi over 2, and subtract the area under cos x from pi over 4 to pi over 2. And that would be fine. It would get us the answer, but it's a lot of work. So it's probably better just to realize that these two areas are symmetrical. So let's just find the area under or between these two curves right here in this interval from 0 to pi over 4, and then multiply it by 2 to get both these areas. So which one is the higher function to start with? That would be this cos function, so I'm going to call that my f of x. So the antiderivative would be sine x. Now this function here would be my g of x then, and the antiderivative of that would be negative cos x. So let's do area under cos x from 0 to pi over 4. And that will be capital F at pi over 4 minus capital F at 0. We put sine pi over 4 minus sine 0. And sine pi over 4 is root 2 over 2, and sine 0 is just 0. Then we will get the area under sine x from 0 to pi over 4, and that would be g at pi over 4 minus g at 0. And g at pi over 4 would be negative cos at pi over 4 minus a negative cos 0. This one would be negative root 2 over 2, and this one would be 1. So we'd have area between curves, and remember we're multiplying by 2, so I'll put that in front. We've got this area here, root 2 over 2, minus this area here, negative root 2 over 2 plus 1. And when we clean this up, we've got root 2 over 2 plus root 2 over 2, and that would be just a root 2. We've got a minus 1 here. And we can leave it like this, or we can distribute it in 2 root 2 minus 2 square units. Find the area bounded between f of x equals x squared minus x plus 1 and g of x equals x squared plus 1 from x equals 0 to x equals 2. Now, when I look at these two functions here, I see that they have some common factors, and so I'm going to try to combine these two functions before I take the antiderivative. Now I just need to know which one is higher than the other. So I can curve sketch or use some test values from 0 to 2. I've got a graph here, and I can see that x squared plus 1 is the higher graph. So that will be the one that I start with, and I'll subtract the other one from it. So I'm going to create this new function, and it will be x squared plus 1 minus all of f of x. And you can see that x squared minus x squared is going to cancel. We've got a plus 1 and a minus 1, and that's also going to cancel. So the only thing left here is the minus negative x, which would be a positive x. And that's going to be a lot easier. Now I can take the antiderivative of that, which would just be x squared over 2. And I can find the area from 0 to 2 of h of x, which would be h at 2 minus h at 0. So 2 squared over 2 minus 0 squared over 2 equals 4 over 2, or 2 square units. Should be able to find area between curves and also determine which curve is higher in any interval. Here's some questions from the textbook. Give them a try. See if you know what you're doing. As Fidge Canop curse.